Welcome to the unit on integration, area between curves and lines. The objectives for this session are to find the area bounded by curves and straight lines. Recall the rule for integrating kx to the power n. If f dash of x equals kx to the power n, then f of x equals k over n plus 1 times x to the power n plus 1 plus c, where n does not equal minus 1. When integrating polynomials, apply the rule for integration separately to each term. If f dash of x is the derivative of f of x for all x in the interval ab, then the definite integral is defined as integral from a to b f dash of x dx equals f of x between a and b, which equals f of b minus f of a. Let's look again at the steps for integrating definite integrals. Write the definite integral statement with its limits, as shown, then integrate and write the integral in square brackets, as shown, and finally evaluate the integral by working out f of b minus f of a. Let's also recall the discussion on the area under a curve from a previous session. The area between a positive curve, the x-axis, and the lines x equals a and x equals b is given by area equals the integral from a to b of y with respect to x, where y equals f of x is the equation of the curve. The shaded area in the diagram in yellow is this area. Let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We are required to find the area of the region bounded by the line y equals 21 minus 3x and the curve with equation y equals 21 plus 4x minus x squared. We begin by sketching the curves on the same graph. Notice that we've factorized the equation of the curve and we've plotted it here. And here's the line 21 minus 3x equals y. The region which we're looking for, or the area of the region which we're looking for, has been shaded in yellow, as you can see. Notice that this is equal to the region below the curve minus the region below the straight line. We're going to denote these areas as area 1 and area 2 respectively. Now area 1 is equal to the integral from 0 to 7 of 21 plus 4x minus x squared dx. We've integrated this term by term to give us the expression that you can see highlighted in red on the right-hand side of the screen. So 21 integrated is 21x, 4x integrated is 2x squared, and minus x squared integrated is minus x cubed over 3. So let's calculate this. Plugging in x equals 7 into the integrated expression gives us the expression shown, minus, and then plugging in x equals 0 into the integrated expression gives us the expression shown here. And tidying up, this gives us 130 and 2/3. So now we've calculated area 1. Area 2 is slightly simpler. Here's the integral from 0 to 7 of 21 minus 3x dx. And integrating this term by term, we obtain 21x minus 3 over 2 x squared. Plugging in x equals 7 in the integrated expression, and we take away from it the same expression with, of course, x equals 0 plugged in. And we tidy that up to obtain 73.5. So area 2 equals 73.5. And the area we're looking for is, of course, area 1 minus area 2. So if we plug in area 1, which equals 130 2/3, and then subtract area 2, which is 73.5. And tidy up to give 57 1/6. So the shaded area is equal to 57 1/6. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. In the diagram denoting y equals x times 4 minus x and the line y equals x, find the area of the region ABC. Now, we can express this region in terms of regions we can calculate. So here's the region we're looking for, shaded in yellow. This is equal to this blue shaded region below the straight line minus the blue shaded region below the curve, as shown in these two diagrams. Again, let's name these areas. The first area we're looking for, we're simply going to call area, and this is going to equal area 1, which is the region below the straight line, and we subtract from it area 2, which is the region below the curve. Now, in order to find these regions, we need to find the point A, because this is the point where the curve and the line intersect. Now, the intersection point is the point at which the curve, with equation y equals x times x minus 4, equals x, which is the equation of the line. And solving for x and factorising gives us the intersection point a equals 3. It can't be a equals 0 because that's the first intersection point and we're looking for the second intersection point. So area 1 equals the integral from 3 to 4 of x dx. And the integral of x is x squared over 2. And plugging in the limits 3 and 4 gives us 4 squared over 2 minus 3 squared over 2. We've plugged in x equals 4 here. and we've plugged in x equals 3 here. To give us 7/2. And therefore area 1 equals 7/2. Now let's find the second area. We're integrating from 3 to 4, x times 4 minus x dx, which is of course equal to the integral from 3 to 4 of 4x minus x squared dx. Integrating term by term gives us that 4x integrated is 2x squared, and minus x squared integrated is minus x cubed over 3. Then we plug in the limits. X equals 4 here, and x equals 3 here. And tidy up the expression to give 5/3. So area 2 equals 5/3. Now that we have area 1 and area 2, we can find the region that we're looking for, or the area that we're looking for. So remember, area was equal to area 1 minus area 2. So plugging in these values gives us 21 minus 10/6, which is equal to 11/6. And we can write this as 1 5/6. This brings us to the end of this session. If you have understood its contents, you should be able to find areas bounded by curves and straight lines. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.